Welcome to Math Minders Academy. If you are new to our channel, we implore you to subscribe so that you become one of our community members. Click the notification bell so that when next we publish a new video, you'll be among the first to get it. Today, we are going to look at exponential growth and decay. And at the end of today's tutorial, we'll be able to learn how to use the formula y equals ab raised to power t, or a equals p into 1 plus r over 100 raised to power t. Now we need to define some parameter using each of these formula. For the first formula here, we look at what is y. Y represents new value here. Y here represents new value. The A here is initial value. Initial value, or you can also say initial amount. Then the T here is time interval. The same thing for this second formula here, it does the same thing. Here, the A stands for new value as well. P is the original value or initial value. Then the R here stands for rate of change. And the T here stands for time interval. Also, if you look at the first formula, we will not define B here. The B here is multiplier. B here is multiplier, which is also the same thing as rate of change. And for growth, we are going to see that B is greater than 0. And for decay, we have the interval for B. B ranges between 1 and 0. Now, before we proceed with the example, we are going to use graph to establish this concept so that we understand each of these parameters that we mentioned that are used to build this formula. Now, we are going to look at, let's take, supposing we have y equals 3 times 2 raised to power s. All right, how will the graph look like? So here, for this particular exponential function here, our a, which is the initial value, is 3. Then we have our b to be 2, and we have our time interval to be s, which is a variable here, which can stand in for any time. Now let's look at how will the graph of this function look like. Why do we call it a growth function? We are going to draw the graph and see how the graph will fare. And that will use that to establish the fact that once b is greater than 0, the graph is going to rise. And we're also going to see what happens when this base value, this multiplier here, becomes less than 1 but greater than 0. The graph will help to illustrate this. So let's look at the graph of that function. So here we want to type f of t equals 3 times 2 raised to power t. And so since t stands for time and it needs to be greater than or equal to 0, so we define that interval for t and condition t to be greater than or equal to 0. So that's our graph. So what do you observe from here? You will discover that this graph is rising. So that's it. It's rising. So from our discussion so far, you can see that here we have, for here, this is A, which is equivalent to what we have. Because look at that. This is where A equals 3. And we see the graph rise. Y, this is measuring growth. This is growth. And also notice, like we said, you take note of B here is equal to 2, and this number is greater than 1. So each time B is greater than 1, or each time we find out that 1 plus R over 100, because this quantity is greater than 1, what it measures is growth, just like we've seen from this graph. Okay? And all the horizontal axis here is the time axis. So we've seen the model of a growth function. It rises from the initial, which is this 3 here. This is the initial. And then, boom, it moves up. So let's see what happens when B is less than 1. Let's find out what happens when B is less than 1. So let's look at another function that will represent decay. So here, if we take g of s or g of t, and we define it as 10 brackets, let's take a number that is less than 1. Let's take 0. Let's take 0.15 raised to power t. And then let's condition our t to be greater than or equal to 0. Okay. So what did you notice? Let's bring out this second function here. All right. So you will notice here, look at this blue curve. You will notice that for this, we also have this as our initial, which is A. And coming here, look at our B is less than 1. And what happened? You see this coming down. You see it coming down. So that represents decay. So you can see that movement towards the S axis or the time axis. So this models decay. So for decay, hence this value of B is less than 1 is going to fall. And then look at the initial here also. 10 is the initial value. So why we see that for growth, the function rises as B is greater than 1. And for decay, the function graph falls as B remains less than 1 and greater than 0. Now, we have put together some examples. Let's look at it. Okay, so let's look at a question. Supposing we are given this question here, we are given that a population, let's take this example now. A population So let's look at our solution here. So here, depending on what we want to use, if I'm using, let's say I represent P to be new population, A to be initial population, then B is going to be my multiplier. So B here is going to be 1 plus 1.15 all over 100. All right. And T is going to be 9 days. So with that, I have this, which is 1,000 into, now let us work this out as decimal. It's going to give us 1.0115. So this is 1.0115, then raised to power 9. Okay, so if we multiply this out, it's going to give us 1108.039. Now this is approximately equal to 1108. So this will be the new population of the bacteria that is increasing at the rate of 1.15% every day. So in the next 9 days, we expect the bacteria to have an additional 108. So this example explains exponential growth. Now we have produced worksheets that captures many questions for students preparing for IGCSE. The worksheet contains different questions drawn from exponential growth and decay. So we are going to look at the worksheet, pick 1 or 2 questions, and the link to that worksheet will be given in the video description. So you can download the worksheet, go through it. Of course, the mark guide is also added to that worksheet. So the mark guide is provided. A link is also made available for you to download it. Go through it and then walk through the exercises, applying the principles that we have taught in this video. So let's look at the worksheet and pick 1 or 2 more questions. Use it to consolidate this concept of exponential growth and decay. So this is the worksheet drawn from numbers, exponential growth and decay. So we are going to look at some questions. Now, let's see question number 1. Question number 1 says, the population of Dubai at the end of 2012 was 2.1 million. This was predicted to increase at a rate of 6% each year, calculate the predicted population of Dubai at the end of 2015. So here, the new value is not known. That's what we are looking for. The old value, that's the old population, is 2.1 million. What else do we know? The rate of growth is 6%. 6% is 0.06. And then the time between 2012 and 2015, the time is 3 years. So now we can look at this. The new value or new population is going to give us 2.1, the old population. Remember, we are using this formula here. We have this. So that will work, any of the two. So we can have 1 plus, since it's increasing, we use addition here. Then we are going to have, already we have divided the rate by 100. So this R over 100 is 6 over 100, which has given us 0.06. So we just go straight and put 0.06 here, then raised to power 3. So that gives us 2.1 into 1.06 raised to power 3. So this gives us 2.5011 as a number. So we can round this up to be 2.5 million. So this will be the population, the predicted population of Dubai at the end of 2015. Now let's look at another question. Question number 2. Robert buys a car for $8,000. At the end of each year, the value of the car has decreased by 10% of its value at the beginning of that year. Calculate the value of the car at the end of 7 years. So here we are looking for the new value. So this new value is not known. I'm going to apply the other formula. And then let's look at the A here is the original price, which is the $8,000. The B is the multiplier, which will give us 1 minus, the rate here is 10%. So we have 0.1. That's 10%, 0.1, and that gives us 0.9. You see that this is decay because of this decrease that we have here. Then let's look at T, 7 years. So if we use this to model it, if we have A, B raised to power T, that is going to give us 8,000 times 0.9 raised to power 7. This will give us 3826.3752. So because this is money, we can leave it to 2 decimal places. We can leave it whichever we can leave this, and we have this. Okay. Of course, if we use this, if we decide to use this, we'll still get the same thing. All right. So we are going to get initial value 8,000. We have 1 minus, this is going to be 10 all over 100 raised to power 7. This is going to be 8,000. Of course, this is 1 minus 0.9 raised to power 7. It gives us 8,000 into 0.1, sorry. This is 0.1. So this gives us 0.9 raised to power 7. And you will see that this is the same thing we got here. And that will still give us the same answer. If you are finding value with what we are teaching, don't hesitate to subscribe to our channel, hit the notification bell so that each time we produce a new video, you'll be among the first to receive it. Share this video. Let us hear from you on the comment section so that your feedback will help us to see how best we can improve our videos to help you and to help other students that are preparing for different examinations. Let's proceed and see if we can take one more example. Now let's look at question number 11. This question is quite interesting. The bacterial population increases exponentially at a rate of R% each day. After 32 days, the population has increased by 309%. Find the value of R. So here we have some things given. We are looking, we do not know the value of R, it's not known. T is 32 days. What else? Then it has increased by 309%. So here we are looking for, of course, the rates at which this happens after a period of 32 days. So we have another one. Let's call this R1 is not known. And then R2 is 309%. Okay. So now we are going to use purely the multiplier. There's no old value, there's no new value given here. So we have a multiplier. Since this is exponential increase, so we are going to use addition here, increasing at the rate of R over a period of 32 days. So this will model that. And then here also, after this, what happens, we discover that the entire population after 32 days has experienced 309% increase. So this is the same as this. All right, so this right-hand side multiplier happens after 32 days. So now we have 1 plus R over 100 raised to power 32 equals, this is going to be 1 plus 3.09. So we have 1 plus R over 100 raised to power 32 equals 4.09. So you are going to take the 32nd root of the right-hand side. So 1 plus R over 100 equals the 32nd root of 4.09. So coming here, we have 1 plus R over 100 equals the 32nd root of 4.09. It gives us 1.045. 1.045. So we subtract 1 from both sides. We have R over 100 equals 1.045 minus 1 R over 100 equals 0.045. So here we multiply both sides by 100, and that gives us 4.5. So the R1 that we are looking for is actually 4.5%. So if the population, whatever the size of population is, if it increases by 4.5% exponentially over a period of 32 days, we are going to have a total increment of 309% of that very population. So walk through the worksheet and then check the mark guide provided. And if there is any issue, go to the comment section and then communicate whatever the issue is, and we will not hesitate to make a video to clear whatever question that you may be having challenges with. So we will be looking forward to seeing you in our next tutorial class. If you have not subscribed, we urge you to please subscribe to our channel. Click on the notification bell so that next time we release a new video, you will be among the first to get it. And this will also help the YouTube algorithm to send this video to as many students as possible. Go to the comment section and tell us how you feel about this video. We are looking forward to seeing you again in our next class, where we'll be discussing another interesting mathematical topic. This is Math Minders Academy. Goodbye for now.
Night glow where the stars align, we lose ourselves in the rhythm divine. Underneath the sky painted with dreams, we're chasing the echoes of silent screams. Caught in the spell of the cosmic night, where fantasies bloom in the pale